We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello dear students, today we are going to study about a very important article, drift and diffusion current. As we have studied earlier, the transition of electrons from valence band to conduction band by leaving a hole inside the valence band. So the possible ways that these charge carriers, which are electrons and holes, can change the concentration are as follows. Number 1, that is the current flow. In particular current flow, we again have 2 dimensions. One is the drift, that means the charged particle motion is in response to an electric field. So whatever will be the direction of the electric field, the particles, the charged particles, electrons and holes will respond to the same. The diffusion. Particles tend to spread out or redistribute from areas of high concentration to areas of lower concentration. So suppose you have higher concentration of electrons in the conduction band and lower concentration of holes in the valence band. So electrons in the conduction band, by losing some energy, will definitely travel to the valence band due to the diffusion process. The number 2, which is the possible way that charge carrier concentration can change the excess amount, is the recombination, from which electron and hole pairs are recombining, which is also known as local annihilation. Generation. Local creation of electron and hole pairs, out of which the major criteria for the present study is drift and diffusion. So what is drift? As you can see, this is the direction of your electric field from negative to positive, and we can also see that this zigzag motion is nothing but the motion of your charged particles, and the direction of net motion is along with the applied external electric field. In the presence of electric field, holes move in the direction of the applied electric field from positive to negative, and electrons move in the opposite direction of the electric field from negative to positive. Motion of electrons and holes is highly non-directional on a local scale, but has a net direction on a macroscopic scale. So here, as you can see, the net direction of electrons and holes is towards the direction of applied electric field. Average net motion is described by the drift velocity. So drift means, first of all, this electron was in steady state. As soon as the electric field is applied, it has diverted from its original position, that means it has drifted with a unit centimeter per second, whereas net motion of charged particles give rise to a current. Given current density, that is J is equals to per unit area electric current, so I upon area, flowing in a semiconductor block with face area capital A under the influence of electric field capital E, the component of J due to drift of carrier is, for holes, Jp drift is equals to Qpvd. Vd is the drift velocity, Q is the charge, and P is the charge carrier concentration of holes. Similarly, you can write down the equation for electron drift current velocity, that is Jn drift, which is Qnvd. Q is the again charge of an electron, N is the charge carrier concentration of electron, Vd is the drift velocity. Here in the direction you can see there is an electric field direction. Holes are moving towards the direction of applied electric field and electrons are in opposite direction. Cross sectional area is centimeter square. At low electric field, we can write down the drift velocity equation as mu into E. So Jp is equals to Qp mu Pe and Jn is equals to Qn mu n E, where mu is the mobility of the semiconductor and it measures how easily the carriers can move through the crystal, where unit of mobility is centimeter square upon volt into second. Thus, from these two equations, we can say that the drift velocity increases with the increasing applied electric field because Vd is equals to mu into E. More generally, for silicon and similar materials, the drift velocity can be empirically given as Vd is equals to mu 0 E upon 1 plus mu 0 E upon V saturated raised to beta upon 1 upon beta, which tends to the equation when there is no electric field apply. Vd is equals to mu 0 into E, where mu 0 is the permeability of free space, 4 pi into 10 raised to minus 7. When extremely high electric field is applied, the drift velocity is nothing but the saturation velocity, and beta, the constant which has appeared in the earlier equation here. So this beta is nothing but the empirical constant. According to Ohm's law, J is equals to sigma into E, that is equals to E upon rho, where rho is the resistivity inverse of conductivity, having the unit ohm into centimeter, and the conductivity is having unit mho into centimeter inverse. Adding the electron and hole drift currents at low electric field, that is, the total current density can now be given as J is equals to Jp drift plus Jn drift. So Q is the common. So we have Q into mu Nn plus mu Pp into E. So this is for drift. Now we will see the case of diffusion. So in order to consider the diffusion, we have to study the Fick's law. So Fick's law describes diffusion as the flux of particles, in our case, is proportional to the gradient in concentration. So F is equals to minus D into gradient of N, where N, or you can say particularly eta is the carrier concentration and capital D is the diffusion coefficient. For electrons and hole, the diffusion current density can now be written as Jp diffusion is equals to minus Q dP into gradient P. Jn diffusion is equal to Q. Now here the negative sign is eliminated because the electrons have the charge negative Q, whereas the holes have the charge positive Q. So Jn diffusion is equal to Q dN into grade N. So according to this, the total current flowing through electrons and hole due to the collective motion of drift and diffusion current can now be written as, for holes, Jp is equals to Jp drift plus Jp diffusion is equal to Q mu P into E minus Q dP into grade P. Similarly, Jn is equals to Jn drift plus Jn diffusion is equals to Q mu n Ne plus Q dN grade N, whereas the total current flowing from the semiconductor is the sum of currents flowing from the electrons and holes, no matter where it is from, either drift, either diffusion, or their collective motion. Finally, you can end up with this equation: J is equals to Jp plus Jn. That means the individual currents of holes and electrons. So this was all about the drift and diffusion current mechanisms. and this question can be asked in 4 marks for your GTU examination. Thanks for visiting this lecture.